Welcome back to Process Dynamics and Control. This next lecture is going to cover control system basics. So fundamental principles of process control. First of all, we think about safety when we design control systems. People, environment, and equipment are all important, and that is a highest priority in terms of safety. The next is profit motive. We want to be able to meet final product specifications, minimize waste, minimize environmental impact or energy use. So there are multiple objectives that we may want to try to meet with our control system design. So we have loose control. First of all, we have a lot of variability in our control, and this might be an operating constraint that we don't want to go above that, and so we purposefully set the set point lower to account for some of this variability. Now, if we think about decreasing that variability, having a controller that can minimize the deviation from the set point, then we could potentially move the set point up closer to an operating constraint. And this difference between the former set point and the new set point, that often equates to a lot of economic incentive for process control. So if we, first of all, are operating in this regime where we have a lot of variability, we're able to control, and after a while, operations or others may be comfortable with moving the set point closer to an actual constraint. Okay, so what we want to see with controller performance, and we're going to be talking a little bit more about what defines good control performance, but one of the things that we can do is relate the width of this standard deviation around a set point. And as that shrinks, as the standard deviation shrinks, then we say that we have tighter control. Okay, so let's go on to terminology for process control, and we're going to use just an introductory example. In this case, we have temperature control within a home that probably many of you are familiar with. So we have a thermostat in our home, a temperature transmitter or sensor that tells us what is the temperature at any given time. And that may update on a second-to-second basis, minute-to-minute, but it's something that's able to measure the temperature and then provide that information to the controller. So the first thing we see is when we write these, the TT, the first thing that is the first letter, that is going to be the measurement. Okay, so that's going to be the measurement, and then the second letter, that is going to be either transmitter. Okay, let me spell that correctly, transmitter or controller. Okay, so you can see here we have temperature controller and temperature transmitter, but both of them are temperatures. Okay, so feedback control is where, so I'm just going to write this, feedback is where the two that you're measuring but also controlling, those are the same. So you're measuring and controlling the same thing. Okay, and feed forward, and we're going to talk a little bit more about feed forward control later, but we're measuring and controlling different things. Okay, so different quantities or temperature, flow, quantities. Okay, so we're measuring and controlling different things. So feedback control, measuring and controlling the same thing. Feed forward, measuring and controlling different quantities or different things. Okay, so we have first of all a set point. So in our home we have the desired, now this is the desired temperature for the home. Okay, so that is the set point, the target objective value that we want to try to keep our home at that temperature. Now we have a system output. When we talk about inputs and outputs, when we talked about that before, we have our system. In this case, the system is the home, and our input is going to be, let's say this this fuel valve, a fuel flow down here. That's our U that goes into the system, and then their temperature is what we're trying to maintain. That's like our output from our system. Okay, so we have our output. We also call that sometimes in PID control, we call it the process variable, or PV. And in model predictive control, we'll be covering some of that later on, that is called a CV, or a controlled variable. But it's really the value that we're trying to drive to a particular target. Okay, and then the system input, or the in this case we call it the controller output. Okay, so CO, or just the output, and that is the system input. Okay, so we'll have a controller here that then the output of the controller will be the input to our system. So that's why we call it a controller output. In model predictive control, we refer to this as a manipulated variable. Okay, so MPC, you have MVs and CVs, and for PID you most commonly have OP, PV, and then SP. Okay, now we also have disturbances that affect our system as well. Now this is something that if nothing changes, our temperature in the home is going to stay most likely at the same temperature or same heating rate for the home. But let's say, for example, there's all of a sudden a windstorm and the heat loss increases, or the temperature outside decreases or increases. You have what are called disturbances, things that you can possibly measure, but you can't necessarily control them. But they're going to affect, the controller is going to adjust itself to be able to maintain this temperature inside the home, even given these disturbances. Okay, so automatic control, when we think about automatic control, you could either have your furnace in your home that you turn on or turn off, okay, manually, or you can set up a controller that senses the temperature, and if the house is cooler than the set point, okay, so then let's see, if the house is cooler than the set point, then we are going to say that we're greater than 0 on this air, and then we're going to open the fuel valve to increase, because we want to increase the home temperature to get up to our set point. But then let's say the house is warmer than the set point, then we are going to go ahead and close the fuel valve to lower the home temperature. Okay, so that's just a very basic automatic control scheme. Now this is called, this scheme right here is just on-off control. And we're going to be talking about different types of controllers. So this is probably one of the most simple types of controllers, which is just on-off control. Okay, so let's draw a block diagram. Now in this case we have a set point. Okay, so that's going to be the set point for our home heating, and let's say we want to in the winter maintain 68 degrees Fahrenheit. Okay, and that number may not change. If you have roommates that adjust it up or down, that set point may change, but for the most part that's going to remain fairly constant. Okay, and then we have a controller air. So this is the temperature of our home. It's the actual temperature, and this is the measured temperature of our home. Okay, so that's a temperature signal. Now these two can be the same, or they can be just a little bit different. Let's say the measurement device isn't calibrated correctly, it could be different. Okay, but this represents our temperature sensor. Okay, so you need three things for a control system. You need a sensor, an actuator, okay, and then a controller. So those are the three things that you need for any control system. So you take the temperature that's measured and you compare that with the set point. So let's say our temperature that's measured is 65 degrees Fahrenheit, and then our controller air is going to be 3 degrees Fahrenheit. Okay, so we have a thermostat that's going to then take that information, and then you're going to have a controller output. So in this case, it tells the thermostat the thermostat tells the fuel valve to open. Okay, so turn on, and then fuel will start to flow into the furnace. And once that happens, the home starts to heat up, and the temperature of the home is going to start to rise. Okay, and then at a certain point, once that temperature reaches, greater than 68 degrees Fahrenheit, let's say it's 70 degrees Fahrenheit, then it's going to then turn off. Okay, so that's a basic control block diagram. Now let's just back up just a little bit for a general control loop block diagram. And in this case, we have, a set point. Okay, we have a set point, and we have, this is always going to be our measured value right here, and then this is going to be our actual. Now we call this also our process variable. We call it Y, and in MPC we call it our CV. Okay, so we take this value, we can convert it into a measured value, compare it to our set point, and then this becomes our controller error that's a function of time. Okay, and then we have our controller output. Okay, now a lot of times we say that this is our COOP for output. Okay, controller output or just output. In MPC, model predictive control, we say it's our manipulated variable. Okay, and that goes to a final control element. Now in most cases in chemical process control, this is going to be a valve. Okay, so it's going to be a valve, or it could be something like a pump, for example, and it could be a couple other things, but it's the final actuator that actually makes the changes. Okay, and then this represents our process. And you may have a disturbance that comes into your process. We sometimes write it coming into the process, other times we just write it coming after the process. Okay, but this is a basic control loop block diagram. Okay, so let's think about a cruise control in a car. So we have a set point, okay, where we want to maintain a certain velocity for our car. And we have our car, okay, and we have a certain velocity as well that or speed for our vehicle. Okay, so that's our actual process variable, and then we're going to have something that converts that velocity into a measured value. Okay, so this is our measurement device or sensor, and then this becomes the measured value of the speed. Now in cars, sometimes they have a thing within the transmissions or the rotational speed of the tires that infers the velocity. Okay, so this is maybe rotational speed or other things that are able to infer the speed. We compare that. I'm going to put a minus sign and a plus sign here just to be able to compare those two, and then we have the error between those two. Okay, then we have a controller. That's our cruise controller, and then we may have our gas pedal. Okay, and then that goes into the car, and then out comes the velocity. Okay, so disturbances for this case, disturbances, you may have hills, wind, curves, passing trucks, other things like that that are going to cause the velocity to change. And then this feedback control scheme is then going to have some error, and then the controller will take action to adjust the gas pedal. Okay, so it does that continuously to be able to regulate and maintain a speed of your vehicle. Okay, so this is just the schematic as we already drew. We just with some our set point, we have our actual car speed, and then we have our measured car speed, final control element, our controller, and our sensor. Okay, and then the actual car as well as disturbances that might be affecting our system. Okay, so this is the basic form of the PID controller. This is the output from the controller, and we're going to have first of all just a bias term, and that is going to be set. Typically it's just when you turn on a controller, it's the current value of that output. Okay, so if you're driving down the road at 60 miles an hour and the gas pedal is set at 40%, then output bias is just going to be 40%, and it's going to remain constant the whole time this PID controller is on. Okay, and then we have KC times an error. Now this is a proportional term. Okay, so it's a PID controller. We have proportional, and then we have integral, and we also have derivative. Okay, so each of these has a unique contribution within the PID equation. This serves to respond immediately to any error. This will integrate over time, so it removes any persistent offset that we may have. And this derivative term, if it's approaching too fast to a set point, it'll slow it down a little bit. Okay, it'll think I'm going to be overshooting my set point. Let me limit the speed of the response. Okay, so one thing to note, we have 3 tuning constants here, Kc, tau I, and tau d. In our PID equation. That's how you tune a controller, is you change those constants. And one thing to note is that Kc is going to be our controller gain. That can be positive or negative. And also note that tau I is in the denominator. So if you make it smaller, this term is going to become much larger. Okay, so smaller tau I makes it a more aggressive integral term and makes the controller more aggressive. Also, tau I and tau d, they have units of time and are always positive. Okay, so always positive for tau I and tau d. Okay, so let's just go with a heated tank example. And we talked just a little bit about feedback control. Now, feedback control is where you measure and control the same thing. Now, in this case, we're trying to maintain a temperature that's coming out of our reactor, and we do that by adjusting the heater rate in our in electrical heating of our reactor. And so I'm just going to draw the temperature transmitter first. This is a thermocouple or something else that is able to measure the temperature that's coming out of our reactor. Okay, and then I'm going to have another circle here, and that's going to be a temperature controller. Okay, and that is going to be then adjusting the heater rate to the reactor. Okay, so this is an example of feedback control, where you measure and control the same things. Okay, so here just in a temperature controller. Now this is, I labeled voltage controller here, but really it's going to be a temperature controller for our reactor. Okay, but let's say a feed-forward controller. Feed-forward controller is where you're measuring and controlling different things. Okay, and we're going to measure maybe the inlet stream coming in. That's going to be a big disturbance here. And so in this case, I would have a temperature transmitter that then would come down to a temperature controller, and then would adjust the voltage going into my heater. Now mostly we have feedback controllers. Okay, you have to have a feedback controller to eliminate any, you got to be able to measure the thing that you're trying to control for most cases. And then feed-forward controllers are typically just added on to feedback controllers to improve the feedback control performance. Okay, so this is a temperature transmitter, temperature controller, and I'm just going to change this from a voltage controller to a temperature controller. We're actually trying to maintain temperature within our reactor. Okay, so you have a final control element. Now, as I mentioned, it can be a valve, a pump. You can also have electrical, controlling the voltage, or variable speed pump. You can also have different types of valves that can either just open or shut, kind of like your furnace example, where it's just on or off control. We're mostly going to be dealing with single input, single output systems. So just one manipulated variable or controller output and one thing that we're measuring. And just the nomenclature, just to review that again, this LT, the first thing is the thing that you're measuring or controlling, and then the second thing is whether it's a transmitter or a controller. Okay, so LT is going to be level transmitter, and then FC on this side is going to be a flow controller. Okay, so now we're going to go over to a class activity, and the class activity is here at the website, at the APMonitor.com website, on the process control course. And if you come down to lecture notes on 3, okay, if you come to lecture notes 3, you'll come to this class activity. So I just encourage you to go through this, ask some of the questions from covering some of the material from today, from the lecture. And then once you're done with that, there's also the activity answers here. Okay, so if you want to go through this, it'll help you review some of the material that we covered for today's lecture.